Structuring systems, an application of basic structural modeling. We're going to continue the discussion of structuring systems and the application of basic structural modeling in this video. This is the next video in this series of structural modeling in discussion. So this video is part of a body of work which is located on my website, and you can see here at this particular, click on this link and it'll take you to the website. The introductory video explains the website, the way the material on the site is organized and how it relates to this video series. And this is my Twitter feed over here, which it's kind of a low volume Twitter feed where I do some announcements. You can ask questions there if you have any questions about the material. So structuring systems or structural modeling was designed as two parts. First, basic structural modeling, which we're talking about here, and interpretive structural modeling, which it uses basic structural modeling to support interpretive structural modeling. And in this particular video, we're going to introduce some fundamental concepts, and we're going to talk a little bit more about how basic structural modeling, the components, may be integrated to support interpretive structural modeling and also structural integration modeling. So this is an overview of the basic structural modeling project slide deck here. Essentially, we're going to have an introduction and give an overview of the slide content. I've added fundamental concepts to this particular slide deck, different from the last video. We'll talk a little bit more about some things that are not necessarily basic structural modeling components, but are ideas and concepts that are necessary to help you understand the way that basic structural modeling is integrated to support interpretive structural modeling and other activities. Then we'll go through the example here, the 19 cities. We'll go through the ordering process, talk a little bit about the process steps, process summary, and conclusions. This video won't make it all the way through these steps. We'll focus more on the fundamental concepts and the basics to the ordering process. So again, here's the overview of what we're going to go through. First, we're going to present the basic concepts and ideas. Then what we've done here is we've taken a set of 19 cities that are in an unordered state, and then we have picked a relationship, which is north of, to map over the set of cities. So when we take a relationship, map it over a set of objects, we have a system. And what was done is the cities were selected at random. Then empirical data is collected to find out, what is the real order of these cities? What does the system look like? Then we analyze. Analysis is then performed to order the cities, and then inference is used to limit the empirical data. So this is really a mixture of empirical data and also inference mechanisms in a manner that reduces the amount of effort it takes to collect the empirical data. So we'll have 25 data points were selected at random. We've ordered the cities to perform the inference operation. Then we do 25 more data points, and then we order the cities to perform the inference operation again, and now we select the city data one point at a time. So this is kind of a little more detailed approach to the process, and it'll hopefully become more clear as we go through each slide in order. So the fundamental concepts that are necessary to get a little bit better understanding of the process and the reasons and the ideas motivating this process are listed here. And we're going the three types of truth that were put forward by A.D. Hall are reviewed, and that's formal truth, factual truth, and value truth. And then we create an approach that uses the same computational system that we develop a system where we can easily integrate formal truth, factual truth, and value truth. And then we use an abstract relation type to organize and integrate these operations. And an abstract relation type really has three sections. It has a marking space, a value space, and an outcome space. And the marking space supports formal and factual truth, and the value space supports value truth. So here's an overview of the three types of truth. Again, this is adopted from A.D. Hall. There are three types of statements that are considered in this discussion: formal, factual, and value. So formal truth is essentially formal logic, Boolean logic, which we're using here, but there's also predicate logic, modal logic. There's all different kinds of logic, but formal truth, or the sentences, depend only on the form of the logical connectives in the sentence. We're going to restrict our use of formal logic here to just Boolean logic. There's factual truth, and the factual truth depends upon the state of the real world. So in this particular case, the factual truth is the real order of these cities. So we're going to use empirical data to find out the facts about how these cities are really ordered, and that's factual truth. And then value truth is an area that is very broad and has many different combinations and approaches, but the value truth itself is determined in a number of different ways. In this particular case, value truth will be used to help in the computational and process, and to help order and structure the cities. But in the phase of the project we're in right now, which is a conceptual solution discussion, the value truth use won't be that obvious. But when we get to the actual solution process, when we're designing the code and outlining the methods and so forth that we're going to use for the specific solutions, then the way the value truth applications will be used will become quite clear. Here's a little bit more of discussion about the types of truth. And basically, here's some examples. So formal truth, basically in this column, factual truth, and value truth. And here's some examples. A is B, John is a man, John is a good man. These are all statements in different forms of truth. And what is really interesting is are they known by experience? So formal truth is really not known by experience, but factual truth is, and value truth is sometimes yes, sometimes no. And so in this particular case, and in the basic structural modeling approach that was developed by Warfield, he mixes these two types of truth. So we have the formal truth and we have the factual truth are mixed in the same kind of operations. So this is a very interesting approach, can lead to great efficiencies in structuring systems if it's used correctly. The abstract relation type was created by the authors to help organize and communicate the processes and procedures necessary to deal with basic structural modeling, interpretive structural modeling, and structural integration modeling. This is a very high-level, conceptual, notional idea of how an abstract relation type works. On the mathematical side, one view you might be able to think about it as, and it has a marking space, an outcome space, and one or more value spaces. And you can really have one or more marking spaces and one or more outcome spaces if that fits your problem. But these are general areas where you perform calculations or you enter data observations. And in these matrices, you can, if you wish, and if it fits your problem solution style, use different types of mathematics in each different form, and then integrate the output from these different mathematics in different ways. So this is really an organizational mechanism that helps structure the processes that you would use to integrate the three different types of truth and the application of these processes to very complex domain areas. So an abstract relation type really has three types. It has prose, which are text and words, has graphic representation, and has mathematics and computer representation. So what we've seen with the value spaces and outcome spaces and so forth are down in the mathematics and graphic representation area. In the formal prose, you can have a formal pattern, you can have informal prose, but you really need to describe what's going on, what the relationships are, what the system set is, and then take a representation of that prose description and display it as a graph and also display it as mathematics. So there's the concept within basic structural modeling and within the structural modeling approach that Warfield developed is called model exchange isomorphisms, which states that these prose description, graphic description, and the mathematics, computer representation, are all isomorphic. You can take the same system and display it unambiguously and very clearly in any one of these specific forms. And not only that, you can also, there's also a very well developed procedure that you can use to transform one form. Like you can take mathematics and transform it to prose, you can take prose and transform it to graphics. So model exchange isomorphisms are a very useful tool in communicating these more complex ideas to large groups of people. Some people will understand prose better than mathematics. Some people understand mathematics better than graphics. Some people understand graphics better than prose. And so this really allows the modeler that's using structural modeling to pick any one of these or all three of these forms, whatever they believe is necessary to communicate to their audience. And model exchange isomorphisms play a very important role in structural modeling. Okay. This particular problem that we're looking at here is the ordering of 19 cities. And what we've done, and what's clearly represented in the documentation that's on the website and other written material produced by the authors, is a system is a relationship that's mapped over a set of objects. So in this particular case, we have a set of cities, 19 of them. We really don't know how they're ordered. The ordering relationship we've picked is north of. And we're going to go through this process and we're going to structure the system and find out which cities are north of the other cities. And we're going to do this in a very stepwise ordered fashion. And the way we've done this is we've identified the cities and we've created a matrix. Then once we have this matrix put together, then we'll go collect empirical data. Only some. We're not going to collect data, all the data about the cities. We're only going to do certain sampling. Then we're going to analyze and order those cities. That will be a way that we'll talk about later on. This is probably where the value part of the matrix or the value space will start becoming clear what we're going to use that for. Then we're going to conduct the inference analysis, and then we'll have a state of the system at that time. It's going to be incomplete, and we're going to need to collect new empirical data. Then we'll do this process again. We're going to analyze and order the cities again. In this particular analytical process is where the value space comes into play. Then we'll conduct the inference analysis and order the cities again. And then after that, we'll just start looking at individual cities that have the highest inference potential. And we won't be randomly selecting cities, because now we have more of a pattern and we can start picking out, well, which one of these would probably give us the highest payback for expending the resources to go get the empirical data. So you just kind of continue this, collect the empirical data, do the inference, order the cities until all the cities are ordered. So that's kind of the ordering process that we'll go through here. There'll be a number of video talks and additions to the slide deck as we go through and work our ways through this. So this is the beginning configuration. We have 19 cities, but I'm on a matrix, on a self-interaction matrix, and the matrix is completely filled with zeros because we have no information, no empirical information about the cities ordering. We know we have a set of cities, 19 of them, but we really don't know how they're ordered. Now the yellow background on the zeros means unknown. It means we have no data about how the relationship between these two items in the set. The red background means false. So we have no empirical information about the cities, but we've said that, oh, we know as a matter of fact that all of the cities that are represented here on the diagonal is false. So why is that? And what this says is city 1 is north of city 1. So logically, we're not going to allow a city to be north of itself. So we know as a matter of fact that that statement is false. City 2 is north of city 2. Well, no, we're not going to allow a city to be north of itself logically. So we're going to fill in all of the zeros on the diagonal with a red background to indicate that actually we know as a matter of fact that that statement is false. Here's our first set of empirical data. We've gone through, we've collected the data, put this together, and now it's just randomly dispersed. And what we really want to do in this case is we want to bring all of the greens into the lower triangular. So from a graphical standpoint, a graphical solution, thinking about a graphical solution for this problem, what's going to happen is all the red zeros should be in the upper triangular, and all the green ones should be in the lower triangular. Now, what we have is we've defined a system as a relationship mapped over a set of objects. So we have our set of objects and we have our relationship, but the configuration of this system is incorrect. We can reconfigure the system and put it into a more correct configuration by swapping rows and columns. We'll swap rows and columns in a manner that maintains the integrity of the system relationship. So here we swap column 5 and 14 and row 5 and 14. And you can see here here's 14 and 5 is down here. 14 is over here and 5 is over here. So you can see 14 and 5. That was this green one. We're going to be moving it over there. And now you can see this is red, and 14 and 5 and down here now is green. So we've moved the green one down here. So this is essentially the process that we use in swapping the rows and columns. So I'm going to go ahead now and just kind of quickly walk through these so you can see that the process now, as we You see that all the red ones up at the top. Now we're moving down and we're moving the green ones to the bottom, to the lower triangular. See, so that more and more green in the bottom, more and more red in the top. This is an effective way to communicate visually and graphically the solution process. Very effective for large groups. Now we've got all the greens in the bottom, all the reds in the top. And this is where I'm going to start this, well, summarizing what we've done so far in this video, which is introduce fundamental basic concepts of structural modeling, 3 types of truth, the abstract relation type, and then the graphical representation of moving everything for a solution into the bottom, lower triangular, all the green ones, all the red zeros will be in the upper triangular. And this matrix here would populate an area in the marking space in the art. And it also contains what? It contains formal truth information. All the red zeros on the diagonal right here, they were determined by logical analysis of the is north of statement. What we said was we will not allow a city to be north of itself, so we placed zeros on the diagonal. So that is logical information, logical truth information. The green ones, that's empirical data. We actually sampled the real world and we found out, is city 11 north of city 2? Yes, it is. Is city 11 north of city 9? Yes, it is. So these green ones are empirical data. Now, the red zero is inferred from the relationship. So if city 1 is north of city 2, then city 2 cannot be north of city 11. So if city 11 is north of city 2, then city 2 is not north of city 11. So these red zeros now, again, are inferred from the relationship. And that is the asymmetric property of the is north of relationship that allows us to fill in the red zeros. So the information that we're going to have in the marking space is going to come from empirical data or factual truth, and also formal truth. So in this particular marking space matrix, we are mixing 2 types of truth in a manner that allows us to more efficiently solve and analyze the problem at hand. So we'll be finishing up this particular video here, and there will be more videos coming in the weeks ahead.